Welcome back to Arxflix. Today, we're summarizing an intriguing paper titled Controlling Text-to Diffusion by Orthogonal Finetuning, or OFT for short. This research tackles the challenge of fine-tuning large text-to diffusion models for specific downstream tasks without losing their impressive generative capabilities. Let's dive right into the essence of the paper. The authors introduce a novel fine-tuning method called orthogonal fine-tuning, or OFT. This method preserves the hyperspherical energy, which essentially maintains the pairwise relationships between neurons on a unit hypersphere. Now, why is this important? It's crucial for preserving the semantic generation ability of these models. Traditional fine-tuning methods either update neuron weights with a small learning rate or add small reparameterized components. However, these approaches often fail to maintain the high-fidelity generative performance of the pre-trained model. There is also a lack of a clear measure to quantify how much of the pre-trained capability is retained. Hyperspherical energy refers to the sum of cosine similarities between all pairs of neurons in the same layer, capturing neuron uniformity. Leveraging this concept, the authors propose OFT, which applies orthogonal transformations to maintain these pairwise angles during fine-tuning. This equation formalizes the goal of minimizing the hyperspherical energy difference between the fine-tuned model and the pre-trained model. By doing so, OFT manages to adapt large text-to diffusion models without altering their hyperspherical energy. To further enhance stability, OFT introduces an additional radius constraint on the hypersphere, keeping the model within a fixed radius from the pre-trained structure. This limits the flexibility of OFT, improving stability and convergence. This figure beautifully illustrates how the radius constraint influences the flexibility of OFT. Smaller values of epsilon lead to a fine-tuned model behaving more like the pre-trained one, while larger values make it resemble the OFT fine-tuned model. The authors demonstrate the effectiveness of OFT and OFT in two significant tasks: subject-driven generation and controllable generation. This example shows that both OFT and OFT can generate stable and consistent images of a subject across different iterations, outperforming other methods like Dreamth and LoRa, which either lose details or collapse entirely. Efficiency is always a concern. OFT uses Cayley parameterization to construct the orthogonal matrix, reducing computational complexity while ensuring orthogonality. By using a block diagonal structure with shared parameters, OFT achieves significant parameter efficiency without compromising performance. In experiments, OFT consistently showed better convergence and stability. It also produced higher fidelity images with more accurate adherence to the given prompts compared to existing methods. Here are some qualitative comparisons. Notice how often OFT deliver high-fidelity images with accurate control signals, outperforming ControlNet, T2I adapter, and LoRa. OFT introduces an innovative way to finetune text-to-image models, emphasizing the importance of maintaining hyperspherical energy. It ensures efficient, stable, and high-quality generative performance without additional inference overhead. This opens new doors for more controlled and effective fine-tuning strategies. That's all for today. If you found this summary insightful, don't forget to like, share, and subscribe. See you in the next video on Arxflix. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.